Hello and welcome to another multivariable Calculus 3 video. Today we will be going over the gradient. Gradient is something that I briefly spoke about in my last video. I want to get more into depth with it, but this video will definitely be shorter because it's essentially an aspect of what the directional derivative is. So the question, what is the gradient? Well, the gradient is the green section in our directional derivative theorem. It is the vector with its individual parts of our partial derivatives. So we have our partial derivative of x, of our function xy, and our partial derivative of y, of our function xy in a vector. That is essentially what the gradient is. Well, how are we going to do this? Exactly what it says there. We are going to make a vector wherein we have the gradient denoted by this del operator of our f of xy, which is just going to equal f sub x, f sub y. And similarly, we can do this with three variables where we have the gradient denoted by that del vector of our function x, y, and z, where we have our f sub x, f sub y, and f sub z. So pretty simple. It really ties in with exactly what a directional derivative is. So I guess the best thing that we can do in this situation is to just give ourselves an example. So our example today is going to be the gradient of f given by f of xy is equal to x e to the y plus cosine xy. If you're thinking that this is a little bit more of a difficult problem, well, I intended for it to be that way. That's why it is, because we already did one pretty simple problem of the directional derivative, and I will be getting more into the application of this within the directional derivative, but we're just going to go ahead and calculate the gradient, and if we have the gradient and a direction and a point, then we can just go ahead and find the directional derivative. I'm blabbering a little bit too much, so let's just go ahead and get this done. We're going to go ahead and it's asking us to find the directional derivative of our function xy, which is going to be our f sub x of our xy, f sub y, xy. Well, pretty simply, we're just going to find our partial x and our partial y. Well, our partial x, hopefully we have some more experience with our partial derivatives, so let's go ahead and do this. Partial derivative of f of x, or our x, is going to be our partial of f with respect to x of our function, x e to the y, plus cosine of xy. Well, let me get this out of the way first. I'm spoiling what I was trying to get going here, but it's kind of in my way. It's bugging me a little bit. Well, what is our derivative of x e to the y, our partial derivative of x e to the y with respect to x? Treating that e to the y as a constant, we're just getting rid of the x essentially, so it's just going to be e to the y. Our cosine xy, well, we have an x inside, therefore we're going to have to do some, I forget the rule. Is it chain rule? I believe it's chain rule. Well, we're going to take the derivative of the outside while keeping the inside the same. So we are going to have minus the derivative of cosine is sine of xy. Take the derivative of the inside with respect to x. Well, just get rid of that x. Now we have a y. So this is going to be e to the y minus y sine of xy. Get some partial derivative practice here while doing the gradient. I warned you guys in our partial derivative video that this is going to be a pretty fundamental topic. Let's go ahead and do our f sub y now. Partial of our function with respect to y, function being x e to the y plus cosine of xy. Well, our e to the y, just taking our x is just a multiplier, so same thing as just e to the y to me. It's just e to the y. What is the derivative of e to the y? Well, it's just e to the y. Our x is going to stay there. Maybe I made that a little bit confusing. It's just going to be x e to the y. Same thing as last time. Actually, the exact same thing, except we're just going to go ahead and switch what exactly we take the derivative of in the inside. Take the derivative of the outside. Well, that's going to be negative sine of xy times the derivative of the inside with respect to y. Well, we're just getting rid of that y, therefore we have our times x. So our partial of y is going to be x e to the y minus x sine of xy. So what is our gradient going to look like? Well, we have our del operator here, a little bit ugly. Our del operator of our function xy. So our gradient of xy is going to equal the vector e to the y of our, so it's our f sub x. So that's going to be this one right here. We have e to the y minus y sine of xy. And our y component of our vector is going to be this right here. We have x e to the y minus x sine of xy. That's our gradient of f given our function. Well, let's go ahead and apply this into our directional derivative. Big surprise here. That's where I was getting. So I guess let's just go ahead and do this. So our directional derivative in the direction of our, that's v, my fault, of our function at 2, 0 is just going to equal what? Well, I stated in the last video that our directional derivative is just this aspect right here, but that is just the gradient of f of xy. So we can essentially write this as our gradient of f at the point 2, 0, right? We can just do that multiplied by our vector v. Well, it looks good. Let's go ahead and, well, we'll compute our gradient first. So our gradient of f of our xy is going to be, I'm just going to go ahead and copy and paste this. It's a little bit long. Oh, man. Got a little bit more than I planned to. Let's see. A little bit ugly. We're good. So then our gradient evaluated at our point 2, 0 is just going to equal what? Well, e to the 0, that is going to be 1. Well, I'll write it out. E to the 0 minus 0 sine of 2 times 0, comma, we have 2 e to the 0 minus 2 sine of 2 times 0. That's our gradient at the point 2, 0. Well, e to the 0, that's just going to be 1. Minus 0 times sine, whatever, doesn't matter. Multiplied by 0, that's going to be 0. So our x component of our gradient is just going to be 1. Okay. 2 e to the 0 is 1. 2 times 1 is going to be 2. Minus 2 sine of 0. Well, sine of 0 is going to equal 0. Therefore, we just have our 1, 2. This is the directional, or our gradient at the point 2, 0. So we have r multiplied by our vector v. Well, let's just go ahead and do that. 1, 2, taken by the dot product of our vector v. 3, 4, 3, negative 4. Let's go ahead and compute that. We have 3 times 1 plus 2 times negative 4. That's going to equal, what, 3 plus negative 8, negative 5. Oh no, we made a mistake, didn't we? I hope you guys caught that. That was a trap. It was a trap. We did not check whether or not our vector v is a unit vector. That is something that I made explicitly clear in the last one. We didn't make sure of that. So let's just go ahead and do that right now. Well, we can already see right now that our vector v is not, it's not a unit vector. Therefore, let's just go ahead and make it a unit vector. I'm going to make, we'll go v hat is equal to our vector v over the magnitude of it. Oop. Well, what's the magnitude of our vector? That's going to be the square root of 3 squared, negative 4 squared, plus negative 4 squared. That's going to equal 9 plus 16, 25. Square root of 25, which is going to equal 5. Well, we can already see that's not a unit vector there. I mean, it's pretty darn clear here. Magnitude is 5. That's not equal to 1. Well, let's go ahead and do our v is equal to 3 negative 4 over our magnitude 5, which is going to equal 3/5 negative 4/5. Now we have our unit vector, so let's go ahead and do the exact same thing. Well, we found our gradient at that point 1, 2, so now it is at 1, 2, so our gradient of f at the point 2, 0, which is equal to 1, 2. So now we can just do this again. We have 1, 2 taken by the dot product of 3 halves, negative 4 halves, or no, 3/5, negative 4/5, sorry. Take the dot product in 1 times 3/5, 3/5, plus 2 times negative 4/5, negative 8/5, negative 8/5. That is going to equal what? Negative 5/5. It's going to equal negative 1. There we go. Well, hypothetically, I explained this briefly in the last video. Let's say you did mess up. Let's say you didn't check whether or not this is a unit vector. Well, hoping that you caught your mistake there, let's just go ahead and take our magnitude that we found here. We can just divide by the magnitude at the very end if we really wanted to. So our magnitude is equal to 5. So that's the incorrect answer, but if you really wanted to save it, we could do negative 5 over 5. Same thing, negative 1. Same answer both ways. One, to me, is more correct than the other. I don't know. Yeah, that's pretty. That's the gradient in the application of directional derivatives. So I just kind of want to get more into exactly what a gradient is. Well, there are 3 main applications that we can do the gradient, and I didn't speak about the y yet. I guess I'll talk about the y up here. So the y, well, now we can, with this, we can find our direction of steepest ascent with our gradient. We can find the direction of our steepest ascent, and we can find our direction of no ascent. Mathematically speaking, it's a little bit more difficult to explain, but in a later video, I'll talk about maximization and minimization within Calculus 3. So I guess that's kind of an explanation for why we have the direction of steepest ascent, the direction of steepest descent. So let me write these down actually first. So we have 1, we can find the direction. Of steepest ascent. Secondly, we can find our direction. Oh man, what happened there? Well, we'll say that it says direction of our. Oh man, did my pencil die out on me? Please tell me it didn't. Let's see here. Sorry, technical difficulties. Come on, pencil. There we go. Let's make this fast. Number 3. So how are we going to do all of these? Well, intuitively, we can just kind of understand that the direction of steepest ascent is just our gradient, right? So, I mean, the steepest descent is maximized with our gradient. So we steepest descent, the direction of that is just going to be our gradient. What is this? F of AB. We'll say AB at that point. The direction of steepest descent. Well, intuitively we can kind of understand that What is descent? Well, it's the negative of ascent, right? I mean, it's the opposite. So, I mean, we can just intuitively kind of understand that the steepest descent would be the gradient of f at that point AB, the negative version of that. In the direction of no ascent, well, what is no ascent? No ascent in a directional derivative is when there's essentially it's parallel. Well, what does that mean? That means that when we're finding our direction of no ascent, we essentially have to have our gradient at that point f of AB be perpendicular to our u. So this is kind of more of a directional derivative kind of context here. I'm sorry if I'm not really explaining this well. It's more in the context of our directional derivative because it introduces our u that we had earlier. It speaks more in the directional derivative sense, but I wanted to introduce it now because it does talk about the gradient, and I wanted them to be their own separate videos. But what I'm trying to say here is that when it's perpendicular, it's no ascent. There's no slope, right? We can kind of understand this when we have like, I don't know, how would I go about drawing this? It's just our slope is equal to 0. I mean, that's essentially what it is. And maybe I should have drawn a photo. I guess it's not too late to save this. I apologize. We're free balling this one. Well, okay. What is our steepest descent at some point? We'll have our point be right here. What's our steepest descent at that point? Our steepest descent is just going to be the positive gradient, so that's going to be there. What is our steepest descent? Well, it's just a negative of that, like we stated here. And what is our no ascent? Oh man, there's no colors I haven't used yet. We'll do a new color today, purple. It's just the first one I picked. Our no ascent would just be this right here. Well, it's kind of difficult to draw because I kind of made it curved. Man, I screwed the pooch on that one, I guess. It's essentially when there's the slope is 0. So, ooh, what happened there? There we go, I guess. It's when it is 0. That is essentially what it kind of looks like, drawn horribly. That is our y, I suppose you could say, just in a gradient only standpoint. That is actually something that the gradient is very helpful for in this class, because there's definitely times where you will be asked to find the steepest ascent, steepest descent, and the direction of no ascent. At some point A, B, this is definitely something that you're going to be tested on for sure. So it's just nice to know this now, how the gradient relates to that. Whenever we hear about steepest, whatever, no ascent, ascent, descent, whatever, that's going to be a clue. It's an indicator to use the gradient here. I apologize for the horrible drawing and the even worse explanation of why these things are the way that they are. Yeah, I mean, I guess that is the gradient. Thank you very much.